appearances, and we manufacture our basalt bar, mesh, and other products in our factory in Wing in Buckinghamshire. We've been in business since 2019 when we started production. We put our own equipment in, which we designed, which is protrusion equipment for taking the fibre and converting it into rebar. So let me give you a background on the basalt. What we do. This is a typical layout basalt. This is basalt in its original form. Somewhat next style. Okay, so as Basalt engineer at Basalt Technology, we have capabilities to build the CBF plants as Carver. This is the continuous basalt fibre plants, which we don't have here, but we are building one in the UAE to all the fibre which we import at the moment. So up to 5,000 tonnes per annum our factory, and we can design it. We have the technology to do that. We also design and build our own extrusion lines, which we have here. Designers built those in and installed them in our Wing site, and the facility we have here is about 400 tonnes a year capacity. It's quite small. Multiply it by about 6. We can get the fact that we're 4.5 times lighter and 1.5 times stronger than steel. So you can say that we're rather more than that, but we can do shift work up 800 tonnes. We can install more lines very quickly. Thanks. This is the factory that we're in. Process looks very much like this. In fact, which is completely finished. We finished in March, but this is a factory producing fibre, 7,000 tonnes a year of the continuous fibre, continuous basalt fibre, and we are in fact here an EPC contractor. So we hand this over to a client. So we are sort of more have the construction as well as the technology to do. We have 12 furnaces there producing the tonnage that we need, and they'll supply us in the UK and supply the Middle East as well. So what is basalt? Basalt rock. It's a common rock all over the world. And what we do with this basalt, and we have to select the basalt that has the correct sort of basis of silicates and different feldspars. But it's basically basalt rock, and we heat it. We melt it. It's melted at 1400 degrees centigrade. It's turned into through a system of melting and extrusion, gravity extruded into fibre, and that fibre is as a filament fibre. It's about 19 microns, and that fibre we use for the basalt rebar that we make here, and we make in the UK. You can also use fibre for other things, or pre-preg, the same as with glass fibre, and it's impervious to salts, acids, alkaline. It operates minus 260 to 700 degrees centigrade. The basalt itself, it's effectively a rock. Next, and this is a quarry that we're actually using in Fujairah in the UAE to supply the basalt that we're having. It's right next door to the factory. We built the factory on a basalt mountain. Next. And this is one of these bobbins are, as the fibre comes into our factory from the manufacturers of the carbon fibre, they come in and then they're loaded onto these racks. Next. And these are protrusion lines here. So when you've got the racks, that one end containing the bobbins, the fibre is then fed into the plant. It's impregnated with resin, epoxy resin, and after it's impregnated, under tension, it's pulled through die box where it's actually dyed, so you get the correct diameter, 16 or 10 or whatever it is. And it goes on to an overwinding mechanism, which overwinds a rib, which then saturates into the bar with the resin and becomes part of it. So you have a rib bust up like you do with steel rebar. And then from that, it goes into the curing tunnels. We have a curing tunnel about 5 meters long, and the curing tunnels run about 180 degrees centigrade, and they cure the bar. So when the bar comes from the curing tunnel into the cooling pool, it's finished. It's a finished bar. It's completely done, and then it goes through a protrusion machine. It's the tractor that pulls it through. It's a protrusion process. It goes through that and it's cut. So we can cut the bar to any length, but mainly up 12 meters maximum, usually because that's a truck length. With 8 mil, up to 8 mil diameter, we can cut. Another close down side. We can do coils. This is an 8 mil bar coiled up in 100-meter coils, which is very good because, you know, that can be lifted by hand, loaded, it's raised, it's stored. And if you're on site, you just let, and it doesn't take a set. Our bar doesn't have a memory. So when you open it, it just springs out. It's like a washing. You want to stand very carefully when you open it out. I've talking to open it up with it. But these are coils. Next one. And then that's one of our clients came over to look at it, and they're picking up the coil there, and this is the coils. Next one. And this is what we call big bar mesh. Now, because you're familiar with mesh and the sizes, and the biggest mesh you can buy off the shelf, as it were, is 2.4, 4.8, A393. And that's because anything bigger than that is almost unhandled on a site. You know, the logistics are, you know, just can't list it. So, but this is a 2.4, 4.8 in 12 millimeter. And here we're making the mesh. We clip the mesh together with a regurgitated plastic lip. So it's rigid. And the next one. And there you are. This is one guy carrying that mesh. So that's a 12 millimeter diamond bar, and it's 2.44. And that will take probably at least 4 people of steel to carry. I mean, and that's how light it is, and how convenient it is, because you can make it to suit. And I'll come around to that in a minute. Actually, go on to the next one, please. Okay, sorry, this is a bit wonky. This is a coil that's of 6 millimeter, or no, like 4 millimeter, with 800. It's about 100 mil pitch. It was sent to the States, so it's actually 5 feet wide and I think 4-inch pitch or something like that they wanted. But it went into a Canadian tunneling project, so it's quite good because they found it much easier to form around the radius of the tunnel. And the next one. And these are stirrups. So these are stirrups, or things that you know in steel. We can make these, and they're made on the protrusion line. We can do shape codes. We don't have a bending line at the moment in the UK, but we're building one in the UAE. It's now in process, and the next one's coming to the UK. So in April onwards, we'll be able to make these in the UK, and we can make bends about 50% of the normal shape codes we can do. And because I just explained that to you, you cannot bend the spar retrospectively. So it's very low modulus, and it's so it can't be bent. You can't put a blowtorch on it and heat it and bend it. So it has to be bent actually at process of manufacture. So you get scheduled shape codes, no problem at all, to actually produce them, providing we know what bends are required. Next. Okay, this is Basalt, BFR bar with Basalt. So that's the trade name, and that's our trade name, registered trade name. So it's all the major points on it. 60% less carbon, embodied carbon. The carbon footprint on this one is 60% less than steel, and it's about 4.5 times lighter than steel, and two times stronger, 2.5 times stronger in tensile strength. And it's completely resistant to alkaline salts. So, salt ingress, marine, it doesn't rust. It's actually non-conductive. It has ideal for, MRI suites in hospitals, anywhere you don't want steel conductivity. It's actually because it's basalt bar, and it's not, it doesn't have to be protected from ingress. You have a 20% saving on your concrete structures, because any external permanent structure would normally have an extra 20% cover allowed within the design. So the design spec plus 20%, that protects the steel as the standard practice, and you'll put it no above it. But you don't need that anymore because you're not protecting steel. So and it's got the other advantages, of course, is that it can be used in different areas of sea, and it can be mixed with steel and replacing stainless, and especially replacing stainless steel dowels. We manufacture to ISO standards, and we have the codes. We have a BBA, British Board of Alcohol BBA certification, and also the ACI AC 45454 building standards in the United States. Can I have the next one, please? So these are the codes. So we've got, this is the American ACI code, ACI 31814 and AC 454, and that covers all the American coding. And I should explain to you that the United States are in front of us on using FRP bar, both glass and basalt, and by about 20 years. So no one uses it in this country, with totally new kids on the block. Since 2019, we've been talking about it. So these are the codes that have been well established, and there is an ACI design code. So designers can use that code to design and do. CSA is the Canadian codes, which are the same as the American codes. BBA is our UK certification. Within our certification testing that we had to do for BBA, UCAS testing, there are design guides, so they can, and designers can use those, but not all the testing. And within Euro codes, which are more relevant to us, there's nothing in the Euro codes now that include FRP bars. So no codes as standard in Euro codes. And in 2024, there will be a revision to include FRP bar. However, within the Euro codes now, there is a clause, it's BSEN 190/2002, it's called an annex, allows more design using by verified testing. So what you can do, what they're saying is that providing you have verified testing, you can use that data to design. So designers, and we're talking to all the designers, and they're now starting getting used to this concept. So I'll come to that in a minute. But so that's the clause within the existing Euro codes. So you can use Euro codes technically with the schools. So this is a case study. This is a National Highways Commissioned trial on the M42 Junction 6. It's a big project, it's an interchange project, and National Highways wanted to see see how basalt fibre bar worked on a regular site, and also they wanted to test that with an AACM, which is low carbon concrete. So we set up the haul road onto the M42s. This is November before last, so it's 2 years ago, and it was it's three slabs, three large slabs. The first slab was a concrete and steel, regular concrete, regular steel, A252 steel, the 8mm bar, and the second slab was like for like A252 basalt with regular concrete. Then the third was basalt bar with an AACM, and the third was an AACM with steel. So 4 slabs laid out. At the same time, we took sample slabs, which were about 2 by 1 meters, and they were sent off to BRE for testing to disruption. And those tests were done early last year, and the report was issued in November this year. So that report is available to everybody, of course. I can send it to you. I'll send it to you, and you can circulate it around, but that's available. And so we had National Highways as the sponsor. We had Skanska as the contractor. We had Tarmac as the supplier of the ASDM. We had us as the Bastec supplier, Basalt supplier, and NCC as the academic partner in that. Next. This is the permanent work. So with that, before it all was temporary, they're going to come out, but this is a permanent structure. So this is a service road that's built along a top of a. Can I go to the next one? There's a service. It's a road that's running along the top of a seawall at Lydd in Kent. If anyone knows where Lydd is in Kent. Yeah. So it's protecting the Lydd marshes and the Lydd ranges from the sea. The seawall was deteriorating. They put a new seawall in, and on top of the seawall, they wanted to run a road. And the EA, we've had some experience with Basalt before, wanted to basically, put their foot in the water properly and say, well, let's use Basalt on this project. So the idea was to design structure, the reinforced structure, using Basalt values. The designer for this was Haskodian, who are clueless on, they've never seen it before. So our own structural engineer sat down with them, and he took the loadings and he designed the reinforced structure. It turned out with an A393 standard with some parts with 150 pitch instead of 200 mil pitch. But what was interesting about this project is that we could demonstrate real how useful it is in a construction site like this, because those bays are 4 meters wide by 5 meters. So we supplied mesh, which was 4 meters wide or 5 meters long, the size of each bay. So that meant, and we put 200 on the truck. Right, now you never get 200 still, but we could put 200 on the truck. And we sent them down to Lid, and all they did, they took them off the truck, and then they dropped them all into position here, each side. And because what you did, you cut down time, cutting, wastage, and most importantly, because you could reduce the concrete cover, we saved 20% concrete. And as an AACN, you know, an AACNs are more expensive. So we saved on the project about £116,000 was saved. And we also, part of that saving was due to the fact that the stainless steel dowels, 20 mil dowels that we used on it were specified. We changed to Basalt. And there was a slight change in pitch. Otherwise, it was 20 mil Basalt dowels used. And so that was quite an interesting concept.
That's the dowels between the slabs.
Yeah, that's exactly, the go between the slabs there. And we had to do some testing on those quickly because the flexible stress on those are different to stainless steel. But we tested them, and with that verified testing, our designer was able to design them within the structure. So that's an interesting project. It's permanent. It's not quite finished yet because they've been held up. They get held up every so many months with the outset nesting time. So I guess you all know about those sort of things. Anyway, so that's that project. Next one. This is the case. I think this is HS2. So this was for. Oh, by the way, I must tell you, the last lid, the contractor was Mackley Van Ord. The designer Haskoning. The supplier of the ASN was Wagners. And we supplied Basalt. So this is HS2 Houston. These are pile guide walls. So, for all the piles they put in there, guide walls. The guide walls, traditionally, they'd use to make the guide walls, which are temporary structures, 20 mil bar as a reinforcement attached to an A252 mesh just to separate it. And it was heavy, and it's a very confined site at HS2 at Houston. Really, there's no room there at all. So they were tight on site and difficult to work with. So we proposed to redesign that reinforcement to make it 16 millimeter diameter bar with 193 mesh. So just brought the diameters down a bit because the way the design works out, we could utilize the tensile strength to the advantage. And what we found, what the fixers found, was interesting again to with the fixers on site, is that they could put 3 of these guide walls in a day, as opposed to 1 in steel, because it's so much easier. And the most important for them was there no hot works application required. So that saved them 2 hours a day. So this is one of the big advantages, and this is the advantage. I keep on talking to people about pricing and everything. You have to look into the logistics and the savings on the logistics. Whilst we're more expensive in terms of the bottom line, meter per meter than steel, we are less expensive overall and health and safety. So that's the client again was cementation, the M&A reinforcements with the specialist guide wall people, and HS2 the main client. Okay, this is Kinnerdocky. This is the Scottish Electric. This is in Kinnerdock in Scotland, and there were sort of several substations they were putting in. And Bam Knuckle were the contractor, and I believe it was I think it was actually Jacobs who were the designers. I'm not sure, I can't remember. Maybe Haskoning, I can't remember. Anyway, it might be on there. I don't know. Anyhow, so what they had, I think 5 or 6, maybe 7 substations, and it's been called for in the design, no steel in the bases. So obviously it was shooting for us. So, but what was great about this is that when we got this, when we got the request, we saw that all these places were different shapes. One of them was a couple of hexagon shapes, a couple of L shapes. So what we suggested to cut down work on site is to make them to bespoke shapes. So we actually shipped those shapes to Scotland, and they just dropped them straight in. Again, cutting all the cutting. There's no cutting, no time, not so much time. Just put just hang them in there and cut it. So that was quite a success, and they're installed now. Next, and this is presently carried on. This is an environment agency as a client again. This is the Esplanade at Canby Island, and it's part of the Thames refurbishment that's going for EA, going right the way down Thames refurbishing. Jacobs did the designs in this case, and we supplied the reinforcing for the replacement areas of the Esplanade. We're taking the old concrete up with steel, and then along the forge new steps, and these steps were made from basalt reinforcing and sem-free concrete from DBG group, and the precast was pound for precast. What was interesting here is that was designed as a permanent structure by Jacobs for EA probably 2 years ago, before we really ever really start talking about it. They came up with it, they looked at it, and they wanted to use it. So this was, and it's in process now, and there's 2 phases done, about 3 phases to do. But it's interesting, and that's that's an ongoing study, and it's a permanent study, it's a permanent structure. Next. I put this up because this didn't go ahead. we did the design, and it's quite expensive to convert this. This is a slab that was for the athlete stroke cup at Houston on HS2, and the idea was a temporary slab to just support some tanks, prison tanks. And the thing is that it was steel design, so we converted the steel design into basalt. So our designer did that, and then presented it back to Skanska, who were the contractor there, SCS, and they had it. They checked it with their designer, their engineers checked off, and they signed it off to go to temporary works. So they signed it off. It wasn't like the permanent works. We didn't have to worry about PI too much. So that went in, and it was going in, and it was all going well, and we were all ready to take the order for it. And then they closed down Houston, Houston, they finished it, so we didn't go ahead with it. But what was interesting is we converted that from steel to basalt design. So what we were able to do when we had some people over from HS2 and from National Highways, when we had a workshop, my design was able to demonstrate to them how we convert basalt. It's really important because it's not the same. It's not like for like. That's why I put that up there, just to explain that. Yes. And these are Canewdin blocks. Now, Canewdin blocks are basically they're square, and some of them are 2 by 1, some of them are 1 by 1. They basically were concrete slabs, 200 mil thick. And what the EA did, the Environment Agency did, they had these made from steel and concrete, regular steel and concrete, and they laid them on embankments and estuaries to basically stop the erosion and prevent erosion. Then great, but the concrete is still there in the seawater or in brackish water. As a temperature that reflects after about 10-15 years, you start to get spalling. So the idea was to change to a sem-free concrete, which is low carbon, our bar, which is of course low carbon and light, and sort of completely resistant to rust. And also a low carbon aggregate, which is quite good. And this was an amazingly low carbon, great result with all the details are here. But what's good about it is that they won an award from the coast last year. So and we were part of it. So it's quite good. And we've got some of these in our factory here, these blocks. Next. And this is just just a retaining wall, but we did the formwork along the base of it just to show you that we can do the beds. Okay, the next one. And okay, so these are just the last case studies. The 2 on the left here are in the United States. They're Horse River Bridge crossing, and there's another one there. But both these are using basalt reinforcement. And they are structures, and they have been designed to ACI codes, and they are used and they're installed, and they're basically working, they're running now, the bridges and those installations. And as I said earlier, the Americans have absorbed this, have taken on board FRP bar much earlier than we have, say 20 years ago. So they've been in the business a long time, they understand it. These are and the Department of Transports in the United States are, most of them are keen to use FRP bar, and certainly Florida. Florida has embraced it more because it's a sort of sea area, and there's a lot of issues it has. So that's them, and their case studies are available. You can download them and read them. And this one here, this is the only bridge that was actually made, built using a span, but having the spans made from basalt bar. It was put up in 2012, not without, I think they imported it from Russia. And Queen's University were the academic partner at, and that was installed in 2011, 2012. And it's since then had a health check in 2018 and performed very well. It's actually working, in fact, better than some of the steel structures and where it's designed and where it's held up. So that's a success story. National Highways, SES guys say, yeah, it was over the river. It's over the river, down under the roadway, but it nonetheless is a bridge, and it was done. And this is another, this is the first job we did, actually. It's a par docks in Cornwall. It's a feed road to the docks, and it's A252, but messing. Next one. And this is our factory that we built in Jera. This is all the bar. What we did, we got the local certification for the bar in Fujairah and in Dubai, which took quite a bit of time, but it was worth it because then we could use these bars in the foundations of the factory. And if you're going to sell bar in your factory that you build, you better make sure that in the foundations you have basalt. What you're selling, otherwise, what's the point? So this was that's the whole
This is the factory.
And this is where these are the foundations. It's 120,000 square feet footprint there. So it was actually for a little while, and when it's flooded, there's a 120,000 square foot swimming pool for about 3 weeks. Anyway, so that's done, and that's up and running. So next one. And this factory, that's a while ago, actually, a few months, it's almost finished now. Next. Okay, this is a project we did, a Dulcet, it's called Dulcet. It was an Innovate UK with BRE, Jackson Civils, DPG, and us. And what it was designing a basalt, a retaining T-section, and we designed it with basalt. We used Senfree AACM. And the idea was to see how it reacts with Senfree, with an AACM, and see how it reacts. Because there's a high chloride content with Senfree, and that doesn't really sit well with steel generally. It doesn't bother basalt. So that was done in 2022. That we finished all the tests on it, testing out, and reports available on this. And it's actually interesting because it's a retaining wall. I've seen the report; it's quite favourable towards basalt bar and Senfree, and it's available. I think it's from January next year. It'll be on, everyone will be up there. Okay, next. Okay, this is the environmental comparison steel. So what we've got is we've got 1.093 kilograms to 0.4. So the difference between steel and basalt is quite thin. And this is actually not weight per weight, because bar we're much lighter. So it really is that difference, because the weights are different. So that's 60% less than steel. Actually, it's more than that, according to some studies. So this is basically demonstrating where the embodied carbon is reduced with using basalt bar. And we have, can we go to the next one as well? And then we have, this is an LCA that was actually published by Kingston University. So an independent LCA by the university, which came to the conclusion that they took 6mm fibre, the FRP bars, Basalt fibre bars, and it came out 74% lower in carbon footprint because they took it from cradle to grave, not cradle to gate as we would. And we have they're still 22% lower than recycled steel, which is the low carbon clean green steel.
Yeah.
But we're still 20% lower than that, and 49% lower than galvanized steel, 88% lower than stainless steel, 44% lower than glass fiber. Glass fiber has other issues. So that's an LCA published, and it's there for everyone to see. Let you have copies of that. Next. I think that's it, actually. Yeah, that's it. So that's the presentation. I think there was a fancy photograph at the end, which took it on. That's the presentation. So if there's anyone like any questions online here, please let me know.
Right, any questions online?
Not yet.
All right, so any questions in the room? Yes, perhaps. Yeah.
Also, I was just wondering about end of life as well.
Yeah, okay.
Whether there's the potential, like steel, to melt it back down and
No.
reuse it.
The answer to that is no. However, what you can do, particularly on the M42 project, which hasn't finished yet, when it comes to finishing, what they're going to do is plane those slabs. And then they're planing the steel ones, and then they have to extract the steel from the concrete. But with basalt, you don't do that. Because it's fibre. What you do, you plane it, and it mashes up into fibre. So we do, with the reusable aggregate, reusable concrete, you just leave the fibre in that. So it remains in the concrete. And sometimes it debonds completely and you get bars out of it, but then you can chop those up. But the major point is that you don't have to worry about the fibre because it stays in the concrete. And sometimes, as we all know, you add fibre to the concrete for crack resistance. And that's what we do. So we've done a lot of tests on this at South Bank University in London, and they've had some really good, interesting results on that. And if you have to put it into landfill, it's inert. The resin is inert, which is potash resin, and what you're doing, putting rock back into rock. So it's not a question. Glass fiber, of course, you can't. Glass fiber, well, you can't. It has nasty chemicals. And steel, well, you have to extract the steel. We had an interesting comment on the exhibition at HUK this year. Well, a couple of the guys said the great thing about it is no one wants to steal it. Because they problems like people stealing the steel bar, and it's like they've got extra security, but they only steal that once, and they find that there's not much value in it. So that's to answer your question.
Thank you.
I suppose the obvious question is from a railway point of view. Does anyone try putting in a concrete sleeper?
Sorry?
From a railway point of view,
Yeah.
has anyone ever tried replacing the steel in a concrete sleeper with it? And testing it under load, see how it reacts.
We never done it, but I think yes, it can be used. It can be replaced. It can replace steel. I think what we need to do is loadings are and what the application is. So what we tend to say is give us an application, and then we'll design it, and then then utilize it. So I don't know all your applications. We've never spoken to it, but rail. We know the rails run on concrete sleepers, and there's all the platforms and there's all the platforms you have concrete, and we know that's what they. And in Holland, they're actually doing experiments with the Dutch railways to do a lot of the platforms using Basalt and other areas. So there's experiments going on. So yes, we can use this actually.
Okay, one step further on from that question was that because everything you showed us was unstressed concrete, but can you use pre-stress or pre-stress or post-stress?
Yeah, you can pre-stress it. You can pre-stress it much like like here, But we haven't done much of that in the UK. At the moment, all that you've seen here, that's not all that we've done. We've done other things, but that's where we mainly use the slab. and some structures and some vertical structures, but there's no reason why you cannot do that.
Because concrete railway structures are pre-stressed.
Yeah, so what we would like to do, that's what I'm saying for the application of it, let's look at the pre-stress and how that, the sleepers, and we can, do a pre-stressed. I mean, I'd like to do it if it's a trial application, really, that's possible. At the end, to try it out, that would be interesting.
In the railway context, for railway overbridges, the possibility of pre-stressed concrete bridges is indeed subject to testing. In a highway context, with the use of salts and other chemicals in their bridges, that's even more an even more interesting application due to the fact that they've got the cover problems in time and the corrosion problems with steel.
Yeah.
So,
Yeah, I mean, I mean, talking about highways, I mean, the SES, the SES guys in National Highways came to a workshop, and what they're looking at applications where they can tiptoe into using Basalt. I mean, I don't think anyone is ready to sort of start using it completely. Everyone wants to tiptoe into the process so they can see it working, and that's what we've done with the Environment Agency. We're doing it with National Highways, Scottish Water, Severn, the HS2 guys. Everyone's using it in areas where they can try it, so that the number one, the contractor, the clients can see it. It's most important. One, your client, your group network rail, but then many times it's a client, and also then there's the contractors themselves and the designers can actually see and get confident in using it. That's really what we're trying to do.
I was interested to see that in one of the early shots, you're able to roll it into coils at 8mm diameter.
Yeah.
Which is in the order, probably with the additional strength of basalt, of the order of all the bars that are required in pre-stressing.
Yeah.
Both the bridge units and of sleeping.
Yeah, I mean, I'd be interested in looking. I'm not really. What you're talking about, I've not seen in terms of this design. So it would be interesting to get that information and talk to our designers about it.
Was there any reason why you limited the 8mm bar to rock coiling it in 100-meter length?
Yeah, because it's quite recording a 10 mil. It's quite a challenge actually. It has a very high. When you bend it, if you bend an 8 mil, I get an 8 mil and I bend that round. But 10 mil, you have to do that. So to make a roll of it, I mean, you could make a coil of it, but to make a mesh, I mean, that's 8 mil is about the biggest we would do.
Yeah.
In a mesh coil. I mean, and really 6 mil, 4 mil is more comfortable, generally speaking. But there's a lot. I mean, don't get talking about a lot of fire strength, tensile strength, still.
I've got a question. What's the fire strength like?
Fire strength is okay. So fire is the issue because it's a fibre. So you can't get away from the fact that it's a fibre and its vehicle. Its vehicle is it's a polymer. So the polymer will at 300 degrees start to soften.
Yeah.
Whereas basalt, so but the actual fibre, there's what's carrying it.
Yes.
And soften. So what you have to do, you have to work out. You may need extra cover to give that time because even still at 400.
Well, steel's not great in fire.
Right. So what you get over is that you put cover over that. So you do the opposite to what you do outside externally. You increase the cover in certain aspects to deal with the fire issue. I mean, and it's always a question where you can use it and where you think the cover is going to be, where it's worth it to do it. And not so.
Okay, thank you. Any other questions? Yeah. Oh,
Could basalt actually totally replace steel with a steel sleeper? Entirely basalt sleeper, like a steel sleeper.
Well,
No concrete.
Yeah, I mean, well, in terms of numbers, probably not for a long time. I mean, that factory you saw there that we built, it's the biggest factory outside China, producing fibre. And if you think that LTC is going to be around about, I think I got the figure I got for their total steel usage. I'm talking about rebar, but LTC is 180,000 tons. we're a long way from it in terms of volume. So to produce it, we can have 6 lines, 10 lines, 8 lines, in that respect. In terms of design, I think there are areas where steel will always be used. I think we're always going to be, again, in the States, they're using it in building construction, in actual buildings construction. They're using it in areas where we wouldn't think of doing it. But to replace steel completely, who knows? I mean, I don't know. I mean, it's already being replaced in a big way with glass fiber bar in the States and with basalt bar, but it's still nowhere near the tonnage because there's not that much made, even in the States. So it could replace steel, probably 80% of what you would use steel for, and 80%, and a lot of steel is slag, as and base work, groundworks. So yes, you could do it, no problem. Even piles. We're making a pile now, trial for again, it's an EA project, but it's for it's a sort of a 9-meter pile, 150 in diameter, and that's the first pile we would have ever made and see how that works. But we like to think about it, but if we got a percentage of 180,000 tons, we'd be very pleased about it.
Yeah, so Malcolm came this afternoon with a little bag of goodies, and they're on the table here in front of James. Perhaps he can just offer a few of those samples round. Be careful when you lift it; it's quite heavy.
Yes, I'll give you some. Yeah. So I said, Randall, I leave these here, so you can take them and put them in glasses. I guarantee you, anyone walks into your office and they say, "What's that? What's this?" And you say, "It's rebar." And it's call it the BN factor. They pick up and go, "Hello, me. What's that?"
Okay. Right. Any more questions?
Malcolm, when I first spoke to you in setting up this meeting some time ago, you were in the UAE and you were building the factory. And when we started, we go, why have they built a factory in the UAE? And it's apparent that it's because you've got a quarry there of the very suitable basalt that you need.
Absolutely. I mean, the quarry, it's on the sort of on the Indian Ocean side of UAE. Is the range of mountains, the Basalt Mountains are mountains. So you've got a whole, and the quarry next to us has I think they've got a mount of 79 million tons available to them. Now, our 6,000 tons a year. I mean, we went to see these quarries, and we said, look, we're going to give you an order for 6,000 tons a year, And then the guy sat there telling me this time, he wasn't really particularly interested. So he said, well, 6,000 tons is morning's work. He said, we do 14,000 tons a day. That's one quarry, and there's about 20 at the moment there. And all that basalt goes as aggregate on roads for Qatar all around the Middle East.
Yeah.
So the owners of that factory, people we're building it for, the company, the Harrow Mining Company, they put down these quarries, and they're getting $6-7 a ton for their aggregate, but they're going to get over $3,000-4,000 a ton when they convert it to basalt fibre. So you can see where that's
I see their interest in it.
and it's in our interest because we never did this before. We built our lines, and frankly, they came over to see us and they saw our production. They said, "Can you build a factory for us?" Like me, a typical salesman, say, "Oh yes, sure, no problem." How did we couldn't be? Well, 2 years later, 3 years later, we are where we are. But yeah, certainly that's why it was built.
So for the time being, the Giant's Causeway is safe.
Yeah, I think so. There's an awful lot of basalt quarries around. I seriously, when we had the Highways UK, especially Highways UK, got a lot of quarry people come because they're there for the aggregates. People that own Tarmac or an aggregate company, and they come on the stand and say, "Oh well, it's basalt. We got no basalt. You want to use ours?" And of course, it wouldn't be a big. I mean, you could actually produce the fibre here in the UK, but it's a big investment. It's a lot of money. It's a lot more money than just putting 2 extrusion lines in, and we don't have a market big enough. So if we had a market big enough, or Europe maybe, then it could be worthwhile. And I think then it would be even better in terms of carbon bottom, because it would be local, very local.
Yeah, you wouldn't have to transfer carbon in it then, would you? So, you say it's completely non-conductive.
Yeah,
So, an application that springs to, looking at Alan, springs to mind is the problems we have with tramways, with DC electrification and stray currents, which cause electrolytic corrosion and reinforcing. So it should be something again, which is,
I think, you know, it's worth you, again, investigating it because it isn't conductive. We're using it, say, in hospitals and, you know, in this particular instance, it would be.
because that's electromagnetic problems, isn't it?
Yeah, that's right. It's not quite the same, but nonetheless, it could be very useful for what you're using it. You've got to remember, you know, the only way from steel and stainless, of course.
Okay, thank you very much. Right, any more questions? Any questions online at the moment?
So what I'd say actually is that all you guys sitting here, if there's any information that you think you haven't got or you need, or you want some more information, or you want to even come down to our factory and wing and see the operation, please let us know. We'd be happy to show you around.
Okay.
And if you can give us an application that you've got in mind, we'd be happy to sit down and look at the design with you, see how we can incorporate it into the Network Rail's general design.
Well, I'll have a chat with the people who are looking, because we're looking at, obviously, like everybody else, we're looking at embodied carbon at the moment. And particularly with concrete sleepers, because concrete's not great material either.
That's right. That's why.
So it's something certainly I'll have a chat with them and see what they're doing at the moment. Well, they may already be looking at this, I don't know.
I mean, if you put an AACN with this and a low carbon aggregate, you know, you're bringing your footprint massively down. So the sleepers, which you have, I guess you've got, I don't know, millions of sleepers you've got all over the country, but if you imagine just all those, you know, being replaced with something that's a really, you know, you're right, you're really, you know, you're getting the 2045 carbon neutral target almost without any problem.
Okay.
So with obviously, with the industry going the way it is, it's trying to go over to BMS carbon and the wellness composite sleeper.
Yeah.
Could this be extruded into a sleeper size?
Yeah, then become called a profile. And I would say it would probably be a hollow profile. I wouldn't call it solid. I mean, solid would be, I mean, you could do it solid. I mean, you can have a solid bar. I mean, instead we protrude this as a fiber bar. A profile is like you have, you know, on your FRP bridges and things like you have it made from FRP, the bridgeways, and they're actually basically hollow section. You could have the same with a much smaller section. You can make it the same. You do the same. You can do the same as you do with your bridge, you know, your bridgeways that you have, you know, lightweight bridges that you have. I know you're using them here and there, but you can do the same with basalt. So you could make a solid sleeper. We make sleepers practically solid, but it would be a hell of a lot lighter and a hell of a lot more durable.
Yeah, the attraction of the fibre reinforced plastic in the bridges is it makes the erection of the bridge and the requirements for the foundations much lighter.
Absolutely.
So it makes the whole thing much more viable. Because the one that we've only got the one up there, we've got some other on the way, but the one at Craven Arms, you can definitely erect it. You can erect that with just an ordinary road rail machine in a few hours. So.
But the way that's made with profiles, you can do with basalt. We didn't go profile. I mean, that's not alternative. We could have gone the profile route, made profiles, but we thought that rebar was the sort of, I don't know, low hanging fruit really, because, you know, it goes rusty and it breaks the concrete. I mean, right now you've got immediately people start thinking, well, that's got to be an advantage. And the actually, when we first started, we actually had to talk about this, the fact it doesn't rust, because that's, you know, the carbon footprint was sort of second or third really. It's then certainly the last 4 years it's become, you know, much more important. So
what is the design life? For what's your design life?
Our BBA certification could give you 60 years, right? But you can extrapolate that, and you have to then, you know, reduce it off and see.
I know it's difficult when you haven't been used to it.
You can extrapolate that out and then work out a design life. In fact, a definitive design, not like still definitive design. 60 years under, but it'll give you the strengths over that period and strength reduction. That's all.
Okay.
But I mean, to go to have a meeting with National Highways, they talk about 120 years. You go off the motorways, you go underneath the bridges there, and they're not even gone for 40 years, and you see falling away, and they know that, so they've got to do something about that sometime.
Indeed. All right. Any questions from online? No, any more questions in the room? Right. Okay. Well, if there's no,
It's fascinating, it's just a fascinating topic,
yes.
and your mind boggles at what is actually the possibilities of such a product. You've gone for the low hanging fruit of making rebar.
Yeah.
Based on the rusting qualities, but one looks forward. If it's a success, and I'm sure it will be, in the right circumstances, that's always the key. But to make a profile of it, knowing that it will be there forever, because 120 years is forever, it's a great prospect.
I mean, that, and also you've got to look at what we call pre-preg, which is textile. So you can weave this like a textile, as you would with glass fiber, and you use it like glass fiber. You impregnate it with resin and you mold it. So for cars, boats, ships, anything where you use glass fiber, which by the way cannot go to landfill, it has to be burnt because
What's the resins?
because of the actual, when they manufacture it, what's inside it, you've got boron, you've got other chemicals to work the process to produce the materials. So they're dangerous. So you can't, but with basalt, because it can do, you can replace both of them. And also it has a high tensile strength in glass fiber. It doesn't have the same high tensile strength as carbon fiber, of course, but it has quite an extensive to glass fiber. So it sits in the middle. Therefore, if you can mix, when you can do hybrid, you can have hybrid boats with ships, boats, certainly racing boats and things like that, and cars, where you can have part basalt, which is a lot cheaper than carbon. So you can actually offset that. So there's a support. And that's a market we looked at with London University. They wanted to do some Innovate UK. But you've got to start somewhere. And
Absolutely.
We started with, this, that, and you guys.
Your first slide showed extrusions and the powerboat, and I'd assumed that they were part of the whole Basalt thing.
But the actual, what we've got, portrait is what we're doing here. What we do when we make a fiber, it's like a gravity extrusion, so it just makes the fiber. The fiber is the secret. Fiber is the filament, which is 19 microns. That's what you're looking at to weave, and that goes to different sources. And I've got samples of the fiber, and it's like a fiber. It's like a woven fiber, and they used it for fire protection because it doesn't have any resin content. It's just basically basalt rock woven.
There wasn't.
Yeah, no,
sorry, this no.
But your very first slide showed there's the powerboat there. There were different sections.
Yeah.
Were they not what you're making as well?
No, we're not. This is just sort of an idea. I think Yuri got carried away when he did the website, when he did this presentation. And we had a powerboat at the end that last. There was a big yacht and a racing car, and everyone said, "Oh, would you make those?" I said, "Well, no." So
We liked it. Yeah.
But no, I think we are where we are with this at the moment, and I think long term, maybe it's certainly in the UAE the thing to start making fibre, right? I think for textiles, because that in China there's a 13,000 ton plant that used our designers designed the technology for the furnaces. The furnaces are quite high, very technical way. I mean, it's got number one in rhodium, platinum bushings that go in there, made from rhodium, and each, very expensive. Rhodium's about $4,000 an ounce, and the design of this is quite complicated. And over there, they produce fibre of a smaller diameter, about I think it's about 11 or 12 micron. And that's for weaving, and they use it all for weapon stuff, for the car industry, for their their automobile industry, airline industry and defence.
Right, if there's no further questions, can I come on ground to propose a vote of thanks?
Definitely. Well, it's weird, it's rare here that you get such an interesting and an informative talk, and I've normally got a half dozen questions written down, and I haven't got any written down to start with.
You're probably thinking tomorrow later.
Yeah, and when we started, we met before the talk, and I think Basalt, that's a rock, you know, and how the hell do you melt rock? And then you said 1400 degrees, and all of a sudden it's clicked on all volcanoes. You know, yeah, that does melt.
Yes,
You know, but everything was there in your talk. Every question I wanted to ask was in there, and fascinating. Thank you. I'm just brilliant. And could we thank that up in the normal way, please, sir?
I was a great audience, and I'm glad it's. I hope that we can go from here, goes on to more.
It's always fascinating to when we have because we try and have a few talks on sort of cutting edge stuff which is really new, and it's always really interesting to see what's going on out there in the big world. The railway industry is quite a traditional industry, and so particularly in the world of permanent way, which is civil engineering type work, it's always good to see something new happening. So, okay, right. So our next meeting is on Monday, the 8th of January, where we have Arthur Emir coming back to tell us how they're getting on with the Global Centre for Railway Excellence. You remember we had a talk about it probably a couple of years ago now, wasn't it? When it was when they were admiring a muddy field in West Wales. Well, now they've actually got some work on, and he's going to give us an update. They got at that point they were still waiting to get the funding, but they got the commercial funding to match the government. So it'd be really interesting to see what that's happening. Okay, so if there's any issues arising from the notes of the last meeting, I'll be surprised if there was, but thank you.
If anybody wants to, I'll watch that rather than look at my notes, because it's just so fascinating as to how it was all prepared in record time.
Yeah.
I couldn't really use 1 page of A4 to write sufficient about it.
No, that was a fascinating talk, wasn't it? Right, so without further ado, I wish you all the best for the season, and we'll see you next year. So thank you very much.
Thank you.
Thanks very much. Excellent.
Yeah.
You got this to help you write your notes at the time. You got this to help you write your notes.
So we did that. That's but all the agencies. I don't know how we avoid.
We can't say because they will have gone now anyway.
Thank you.
It's good because it's the internal camera. Effectively, I'm using this instead, so it turns everything around. There's probably a fancy way of doing it.
You know, you speak for it.